So my name is Joe Abley. I work for Internet Software Consortium, and I'm here today to talk about nothing whatsoever to do with ISC. This is really just a very brief summary of some issues surrounding PGP for those who are not familiar with it, to be sort of consumed in conjunction with the key signing party and with ad hoc key signing that you may decide to do with other people who have red dots on their badges. So that's what this is about. There's nothing groundbreaking here. It's more tutorial than revelationary. So there's a couple of slides here about some bad things that happened this year. This is by no means an exhaustive list of all the bad things that happened in July and August. Just some brief examples. There was an advisory issued in July for a bug which had potential to cause widespread disruption amongst Cisco routers deployed in the internet. And certain operators got pre-warning of this bug by a couple of days because there was concern that if the network was widely disrupted, then people wouldn't be able to download patched code in order to upgrade their routers. So people like root server operators and large network operators got some pre-warning of exactly what this bug was all about. And some of that was done in face-to-face meetings, but an awful lot of it was done on phone calls and by email. So some bad things that happened in August. There was a particular FTP server in Calgary which was compromised, and a Trojan version of OpenSSH, the OpenSSH portable tarball, was loaded onto that FTP server. And that FTP server is actually the master server for OpenSSH. It's the ftp.openbsd.org. It's the Sunside mirror in University of Calgary. Sometime, I think briefly before that, was announced, the FSF, announced that ftp.gnu.org had been compromised sometime in March. And the fact that it had been compromised hadn't actually been identified until a week or two before the announcement they made in August. So the potential there was that software from that FTP server may not have been genuine as intended by the people who uploaded it originally. So with those kinds of events in mind, it occurred to me that it would be nice if it was possible to actually communicate using email and have some confidence, even without encryption, that the people you're talking to are in fact the people you think they are. It would also be kind of nice if we could download software and be confident that the thing we actually downloaded was the thing that we expected it to be and hadn't been modified somewhere between the developer and the machine we downloaded it onto. So in some wonderful future universe, wouldn't it be nice if we could encrypt conversations with people to discuss ad hoc operational issues? So these aren't destinations for email that are people we talk to every day. These are just random people we might suddenly have an issue with. We might want to send someone some email maybe once in 5 years. We've never met them before. But it would be nice to be able to encrypt things in an ad hoc way and have some sort of indication that vaguely sensitive data is being protected from trivial observation. Similarly, transferring customer lists, billing data, logs, packet captures and things without having to send them in the clear would also be an advantage sometimes. So in thinking about this, these are the requirements that I came up with. The ability to authenticate the origin of arbitrary data, so data signing, seems like a good thing if we could do it. The ability to encrypt arbitrary data such as the plain text will be obscured from casual observation would also be handy. And presumably we'd like to be able to do it in a way that doesn't make our heads hurt too far. We don't want to have to take aspirin every time we do one of these things. And the motivations here are trying not to install software that we're not sure of the origins of, particularly software that might be of some strategic risk to the rest of the network. If many things depend on one bit of software, it's nice to know that that software is behaving as we expect it to. And also to be able to send secure email to other people. I mean, I've worked for some reasonably large network operators, and it's trivial to send, well, it's usual to send all kinds of information by email in the clear between people in the same company, despite the fact that email is being forwarded to all kinds of external accounts and to wireless devices and all kinds of things. And even sending internal company mail frequently results in mail being sent in the clear across wireless networks. So assuming that internal mail is internal is not usually a good assumption. So PGP, for the 2 or 3 people in the room who may not have heard of it, it stands for Pretty Good Privacy. It's originally written by Phil Zimmerman. It was subsequently developed and distributed by other people, and the GPG is a compatible, free alternative. So what does PGP do? PGP includes some key management tools, as well as some tools to sign and encrypt data. So it does the kinds of things that we're talking about. Some modern mail clients have workable integration of PGP functions into the mail client. The quality of that integration varies greatly. And public key servers have existed for a long time, and they have a lot of keys on them. So some of the elements for providing this kind of infrastructure, where we can meet some of those, wouldn't it be nice ifs on the previous slides, are already in place. So the other principal feature of PGP is that it's designed to allow key distribution via public non-secure means, while still providing a means to verify the integrity of keys by those that want to use them. So this is done using signatures. So if A signs B, it implies that A has some level of trust in the authenticity of B. And then we have this thing called the web of trust, as subsequent keys are signed by not necessarily the end users of a particular conversation. So in this example here, if I want to send some mail to Rob, and I want to PGP sign it, or I want to encrypt it, I don't necessarily have to have met Rob before and have some sort of confidence that I have his key through some secure exchange. If there's a chain of trust through intermediary keys, I can gain some degree of trust in the key that I want to use to talk to Rob without having to actually have met Rob at a meeting or anything like that. So if there's a chain of trust from a key that I trust, which is my key, to Rob's key, which I don't know anything about, we can establish trust through this pattern here. Paths through this web of trust are frequently asymmetric, so if Rob wants to send a reply, the keys that he looks at in his keyring to determine whether he trusts my key might be different to the A, B, and C keys on this diagram here. And path diversity here is good, because, for example, if key C in this diagram becomes compromised or useless in some other way, or I discover that the person responsible for key C is more or less signs anything for fun, and the actual trust implied in that is not great, it's nice to have another path so I can avoid using key C. So there are lots of operators in the world, and the chances of meeting all the operators you might ever want to send ad hoc mail to in a single meeting is close to zero. But however, the number of people who do go to lots of meetings provides some sort of relatively small path distance through the web of trust if people routinely signed keys and kept the keys up to date. So as it says here, there's a large number of people who know someone who does come to NANOG, or knows somebody else who knows somebody, and so on and so on. So building a web of trust which is dense and reliable doesn't seem like a completely unreasonable idea. It's not like you have to be able to meet everybody you have at every company you want to exchange mail with in order to be able to use PGP, as long as there is some degree of key signing happening on a regular basis. So aside from all these positive aspects, things like we have the software installed and we know how to use it, and we can find public keys from key servers, we can verify signatures, and we also happen to be talking to somebody else who has published a public key and also has PGP software installed and knows how to use it, and can also find keys for us and intermediate keys, there are still some issues. We rarely have a good way of verifying that the public keys we have found are in fact the right ones. There's lots of keys you can find for lots of people on lots of key servers which have either different origins from the person you think made those keys, or they were made by people who subsequently lost their secret key and can no longer use that key. People's keys expire. People frequently think it's a good idea if I put a key on the key server, particularly when I've already had an experience where I lost my secret key and therefore can no longer use the key and can no longer revoke it, I'll put a time limit on my key. So my key will expire in 2 years. And if you look on the key servers, there's a very large number of keys there where the only keys for individuals are expired keys, because people are not renewing their keys and re-uploading them to the key servers. And an expired key, of course, infers some lower level of trust than perhaps you might like. And the other thing is the public key servers are public, so anybody can upload keys. Anybody can upload a key to the MIT key server called jabbly@isc.org, and there's nothing to stop them doing it. So relying purely on the tag, on the name of the key, on the email address in order to infer trust is a bad idea. You need that web of trust. So here's an example of where some of the pieces fit together and yet the result is not exactly satisfying. So there's this FTP site here at the top that some people may have seen before. And there's a software called Bind9. So in this example, we're going to download this software called Bind9, and we're going to sort of try and verify that the thing we downloaded is in fact the thing we expected to find. So we download the thing from this FTP site. We download the detached signature, the .asc file. And then we use GPG to try and verify that that signature does in fact sign that data. So the data and the signature correspond. So it turns out that's what you type, GPG minus verify on the top, and you see some output there. So we found out that the signature file we downloaded corresponds to the tarball that we expect was used to generate that signature. And we found that key on a public key server, and that also matches it, so that makes us feel good and things like that. But at the end of the day, what did we prove? We don't actually have any trust that that key we downloaded from the public key server is in fact the real key. We know that it matches those other things. We know that the tarball signed with that key that we don't trust was signed reliably with that key because we downloaded both of them together and the signature matched. But if ftp.isc.org has been compromised, then if somebody can install a Trojan tarball, they can also make a signature and install that. So we haven't actually really proved anything. So we don't really know that what we downloaded is what the Bind developers actually published. So what's missing here is that web of trust, the chain of trust that allows us to trust this key, this PGP key at isc.org with this particular key ID. So to make these little bits and pieces which do exist and do work actually sort of expand to finish the job and satisfy some of the requirements in the earlier slide, we need to encourage people with whom we want to talk to actually take the effort to install PGP software and use it and try and understand it. Because even if we have a web of trust, if the other sort of possible endpoints of that path through the web of trust are vanishingly small, only 1% of operators have a published key, then we only have a solution for talking to 1% of operators, and that's 99% useless. People should sign software so people can verify that it hasn't been tampered with, because even if we have a web of trust, if the software is not signed, obviously we can't verify anything. Uploading keys regularly and signatures to key servers needs to happen. Try to renew keys to make sure they don't expire. That also has to happen. If all the keys are expired, then again, the situation is less than helpful. And strengthen and expand your personal web of trust. So as far as key signing economics is concerned, if your key has signed a lot of other keys, then that's a useful key for people to know, because it's a useful sort of node in that directed graph of trust, which allows us to reach many other endpoint keys. So if I trust your key, I will sign it. And if lots of people sign your key, paths to your key will be short and diverse, and it's easy to use. So the greater the path density and the path diversity through the web of trust from your key to other people's keys, and in both directions because it's asymmetric, the more useful your key is, and the more likely it is you can send mail to other people that's encrypted, and the more likely it is other people can send mail to you. And as well as sending mail, if you're a software vendor or a free software publisher, same thing. The more likely your key is to be able to talk securely and with a degree of trust to other keys, the more likely it is that that signature on that tarball will be useful to somebody. So here at this meeting, we have red dots on badges. And if you don't have a red dot and you would like one, I'm guessing there's more at the registration desk. I'm sure there's lots there. So if you see somebody with a red dot on their name tag, that means I sign keys. So if you go up to a person who has a red dot and you give them a copy of your public key fingerprint, which is a small ASCII string of hex digits, quite small. I have on a business card, lots of people do. That allows them, if they know that and believe you are who you say you are, to somehow later look at the fingerprint for the key that they obtained from somewhere else, like a key server, and verify that it's the right key. And if they put a signature on that key, that means they and other people who trust their signatures can then infer that trust at later times. So if somebody gives their fingerprint to you, and you are confident you know who they are, you can sign their key. So this sort of thing can happen in corridors just by looking at people with red dots on their badges. It doesn't have to be at an organized event. The other thing at this meeting we have is a key signing party, which is tonight, 9 p.m. in Salon F after the BOF is finished. And that URL there contains some information about the key signing party, which is a sort of more organized group event corresponding to the corridor event. So if you're interested in participating, the website actually says you should send your ASCII armored keys to me before noon, which only gives you 10 minutes. So I figured 6 p.m. was probably a more reasonable deadline. So,
how do we know that jabley at isc.org actually will reach you?
You don't, and you don't need to. In fact, the worst case scenario there is you turn up at the key signing meeting and your fingerprint is not on the list, not on the sheet.
How do you know that? Well, no, never mind.
And that is the end. Thank you very much.